So this experiment is HC refrigeration system. HC means hydrocarbon refrigeration system. So you are going to conduct the load test on the refrigeration test rig, and you are going to determine the coefficient of performance of this refrigeration system. So you need 4 thermometers and 1 stopwatch for conducting this experiment. So you have to fill the chilled water calorimeter with pure water so that the evaporative coils are fully immersed. So you will be having a provisions for thermometers. So here on provision, from this you can measure the value of T3. Here is there on provision, so you can measure the value of T2. So here the provision is for measuring T1, and here the provision is measured the value of T4. So this is the condenser temperature, this is the compressor temperature, this is for expansion valve temperatures, and this is the evaporator temperature. So select the thermostatic expansion valve line by opening the shut-off valve and this line and the closing the one of the capillary line. So either you can use capillary tube for conducting this experiment, or you can use solenoid valve for conducting this experiment. You have to choose either any one of this. Then you have to start the compressor and you have to run for some time so that the chilled water temperature is lower to the given test temperature. So now I am going to on the compressor. So compressor you are going to switch on, heater is on. So then I am going to on solenoid valve, mixer and the cooling coil. So here you can measure the cooling coil temperature. So it will take some time. So it will show the value. You have to reduce the temperature of the cooling coil to the given temperature. So for that only you are going to measure the coefficient of performance. For that only we are conducting the performance test of this experiment. So the temperature, now we have switched on all the heater is switched on, compressor is switched on, and chilled water temperature can be noted here. Then the temperature in the water calorimeter, it is allowed to reach the equilibrium temperature. So this cooling coil temperature has to come to an equilibrium temperature. So then you have to connect this energy meter to the motor and the heater by selecting switch one after another and note down the time for 10 revolutions of the energy meter disc. So for every 5 blinks or 10 blinks you have to measure the energy meter reading. So then you have to note the pressure values. So from this P1, P2, P3, P4. So are the pressure values we can measure from here, and the values of temperatures can be taken from the thermometer values, that is T1, T2, T3 and T4 from the normal thermometers. Then after taking these readings, so you have to wait for steady state conditions for equilibrium temperature on the cooling coil. After that only you have to switch off the heater and all the mains. So here you can note the value of equilibrium temperature of water. Then pressure values P1, P2, P3 and P4. Then temperature values T1, T2, T3 and T4. And enthalpy values can be calculated and noted here H1, H2, H3 and H4. These are the formulas required for conducting this experiment. State 1 which is indicates the entry of the compressor. State 2 means exit of the compressor. State 3 indicates the exit from condenser. State 4 indicates the entry to evaporator. So 1, 2, 3, 4 these are the descriptions for that P1 to P4 and T1 to T4. So P means we know its pressure, T means temperature, H means enthalpy, small v which is specific volume. So N means number of revolutions of energy meter disc, T1, T2. So these are the time taken for N revolutions of energy meter disc for heater, T2 for the compressor. So K which is the energy meter constant which is 1200 revolutions per kilowatt hour. Capital N is the speed of the compressor which is 2850 rpm. H1 is the specific enthalpy of vapor, so corresponding to PE and T1 you can take the value of H1. H2 is the specific enthalpy at PC and T2 assuming isomeric compression process. H3 is the specific enthalpy at PC and T3, and H4 can be taken as equal to H3. So stroke volume of the compressor can be measured by pi by 4 d square into L. So then average evaporator pressure which is P1 plus P4 divided by 2. So that value is PE. And average condenser pressure can be calculated from PC which is P2 plus P3 divided by 2. So after calculating this, we can calculate the heater input. So that is QE equal to N by T1 into 3600 divided by K, which is in terms of kilowatt. Then compressor input, which is W equal to N by T2 into 3600 divided by K in kilowatt. Actual COP is heater input divided by compressor input, which is QC divided by W, which is also equal to T2 by T1. So we can calculate the theoretical COP by H1 minus H4 divided by H2 minus H1. Then refrigeration flow rate M can be calculated by QC by H1 minus H4 in terms of kilogram per second. So next, theoretical swept volume displacement, which is Vs, can be calculated by pi by 4 d square into L into N by 60. Then actual refrigerant volume displacement Va equal to M into V1. And finally, volumetric efficiency of the compressor can be calculated by Va divided by Vs into 100. So finally, you can note the values of, after calculations, you can get the values of actual COP of the system, theoretical COP of the system, and volumetric efficiency. Finally, you can also note the values in this tabular column, which is PC, PE, time taken T1, T2 values, QE, W value, COP actual and theoretical values, mass flow rate of the refrigerant, Vs and Va. So finally, you can get the value of volumetric efficiency.